So Z transform is given by the equation n is equal to minus infinity to plus infinity xn z raised to minus n. Right? This equation is called as the bilateral Z transform, whereas the equation with a small modification in the limit tending from 0 to infinity xn z raised to minus n is called as the unilateral Z transform. Now why unilateral Z transform and why bilateral Z transform? Why these names? Right here the signal xn extends from minus infinity to plus infinity. It means that it is taking values on the negative scale also and on the positive scale also. And therefore, we call it to be bilateral, means having both the polarities. That's why bilateral Z transform. Whereas unilateral Z transform means the signal xn is extending only from 0 to infinity, positive values of n, and therefore you call it to be unilateral Z transform. Okay, so we have equation of Z transform wherein if the limits are minus infinity to plus infinity xn z raised to minus n, you call it to be bilateral Z transform. If the limit goes from 0 to infinity xn z raised to minus n, only positive values of xn, you call it to be unilateral Z transform. Okay, so this is the basic equation of Z transform which we will be using throughout this chapter to analyze or to find out the Z transform of the given signal. So as discussed earlier, let us quickly list out why we are going into Z transform. I have already told you, I have already discussed with you all the benefits of Z transform, but let us now quickly identify few more merits of Z transform that will give us a motivation of why we are having this particular chapter into the course. So Z transform is applied for the analysis of discrete LTI system. So as I first told you, the very first thing about Z transform is that it is applied on discrete time domain signals. Remember, Z transform is a tool that can be applied only on discrete time domain signals. You cannot apply Z transform on continuous time domain signals. Okay, this is a very important thing that you should understand, that Z transform is applied only to discrete time domain signals. Okay. The next property. What is the next property? Is the Z transform is an important tool that is fundamental to filter design and system analysis. As I told you, you're going to study the subject called digital signal processing ahead, in which you're going to study digital filters and system analysis. So when you're going to do digital filter designing, Z transform plays a very important tool there because it helps you to analyze your discrete time domain signals. So Z transform is commonly used throughout in the analysis of filter design. Okay. Z transform is very useful and important technique used in the areas of signal processing, system design and analysis and control theory, right? So wherever discrete time domain signals are involved, Z transform is commonly used mathematical tool there. Okay, all digital signal processing systems, okay, involves the use of Z transform. So let's look at the fourth property, the fourth merit now. It will help you to understand the behavior and stability condition of the system. This is very important, right? It helps you, Z transform basically helps you to identify the stability of the system, as Laplace transform help you to identify the stability of CT signals. Similarly, Z transform can be used to identify the stability of the given discrete time domain systems. Okay, you can identify the stability of the DT system by analysis of its Z transform. Okay, if you take the Z transform of those signals, input and output signals, you can easily comment on the stability of the system. Z transform is extensively applied for analysis and synthesis of several digital filters. Right, so as I told you, when you study digital filters, Z transform, there is no alternative to Z transform. You have to use Z transform in the analysis of digital filters. Z transform is utilized in many applications such as linear filtering, linear convolution, cross correlation, and various such mathematical operations. Right? Z transform helps you to simplify such kind of mathematical operations that you're going to do on discrete time domain signals. So Z transform is commonly used throughout. Okay. Systems can be characterized into stable, unstable, causal, anti-causal using Z transform. Okay, you can easily comment on the stability of the system. You can easily comment on the causality of the system using Z transform. Now, how can you use Z transform to understand stability? How can you use Z transform to understand causality? Right? We will study all this as we go into the depth of the chapter. Okay, now let us look at interesting things called as a Z plane. Okay, let us look at Z plane. So, as I told you at the start, we have Laplace transform, right? In Laplace transform, we use the variable S. Similarly, in Z transform, we use the variable Z. In Laplace transform, you have S plane, where the real part is sigma, imaginary part of S was j omega. So sigma plus j omega is a representation of the S in S plane. Correct? Real part is sigma, imaginary part is j omega. So with this sigma and j omega, you draw the S plane in Laplace transform. Similarly, we have a Z plane in Z transform also. Okay, we have a Z plane. So what are the axes of the Z plane? So you could see here the axis of the Z plane is real part of Z, and the Y axis is imaginary part of Z. So it is real part of Z versus imaginary part of Z, right? And what does a Z plane comprises of? Z plane comprises of a unit circle. Z plane is actually consisting of a unit circle. Everything, the stability is commented on the basis of this unit circle. Okay, so Z transform, let us look at the points here. Z transform possesses both real part and imaginary part components. The way S plane has real part and imaginary part, even Z transform also has real part and imaginary part. Okay, therefore a diagram of imaginary component against the real component is titled as the Z plane. So imaginary part versus real part is called as a Z plane. Okay, and the radius of this unit circle in the the radius of this circle in the Z plane is a unit. It's 1, and that's why it is called as a unit circle. Okay, this is called as a unit circle. And this circle and this analysis of this Z transform with respect to this unit circle will help us in determining or commenting on the poles and zeros, and then on the stability of the system, right? We will look at poles and zeros on the stability of the given discrete system, the Z plane. Okay, so I know friends, it is difficult to understand the things at the very start, but as we go into the depth of it, we are going to use this. We are going to plot these Z planes, and then they will understand how the things are being correlated with respect to Z plane and the stability and the causality of the system. Okay, so this is all about the introduction of Z plane, about Z transform, which is region of convergence. So Z transform defined without this region of convergence has no meaning. So region of convergence plays a very crucial role in Z transform. Right, now what is this region of convergence? So region of convergence is those values of Z which keeps the Z transform finite. I'll repeat, it says that region of convergence is those regions or those values of Z for which the Z transform is finite. So this region of convergence should be defined for all the Z transforms, right? So without ROC, without defining ROC, Z transform is incomplete. So Z transform should always be defined with ROC. Right? So ROC needs to be completely defined whenever we find the Z transform of any given discrete signal. So what are merits of region of convergence? So it helps us to determine the stability of the system. It also helps us to determine whether the system is causal or anti-causal or non-causal. So causality can be determined from ROC. Stability can be understood by the ROC, and even from the ROC, one can understand whether the signal is finite or infinite in length. So all this analysis can be done by just observing the ROC. So ROC plays a very important tool whenever we are analyzing the signals using Z transform. So remember that whenever you find the Z transform of any signal, you are expected to find the region of convergence accordingly. So let us now solve certain problems on Z transform. Okay, so here is the first problem statement. It says find Z transform of the following signal. So whatever theoretical discussion we just did, we can understand it in a much better way when we start to actually apply it. Correct? We start to understand what is Z transform, what is the ROC, right? What is Z plane? How do we utilize a Z plane to understand stability, causality? All this is what we'll understand when we'll actually solve certain problems on it. So let us look into more details about the concept of Z transform through some numericals on Z transform. So the first problem is find the Z transform of a discrete signal. So we all know that this is a discrete signal having 4 samples. There's no arrow mentioned here indicating that by default the first sample is located at 0. The second sample is located at 1. Third sample is located at 2 and the fourth sample is located at third time instant. Correct. So with this information about the input signal, let us find its Z transform. So Z transform is given by the equation I just seen, minus infinity to plus infinity xn z raised to minus n. Now looking at the given xn signal, we can find out what should be the limits. So we know that xn extends from 0 to 3. Correct? Xn extends from 0 to 3. So substituting the region where xn is actually existing, it changes the limits to 0 to 3. Xn exists only for the time instant 0 to 3. Now we'll expand this summation for various values of n. So starting with n is equal to 0, we get the first expansion as x of 0 z raised to 0 plus, summation indicates plus, putting the next value of summation n is equal to 1. Now we get x1 z raised to minus 1, x2 z raised to minus 2, x3 z raised to minus 3, right? So this is the expansion for the given summation. Now let us put and substitute what are the different magnitudes of the input signal at these different time instants. So x0 is 1, z raised to 0 is also 1. X of 1 as we see here is 3, x of 2 is 5 and x of 3 is minus 2. So accordingly we have substituted and this is the Z transform of the given sequence. As I said, Z transform without ROC is having no meaning. So we need to find ROC. Now the ROC that we just discussed, what ROC is defined? ROC is defining those values of Z, right, which makes your Z transform finite. So we need to identify here which values of Z is making our system infinite, right? Let us find out those values of Z which makes our Z transform infinite. So since the powers of Z are negative powers of Z, we understand that if we put a value of 0, if we put Z value as 0, right, Z value of 0 will make the system, will make the Z transform infinite, because 1 upon 0 the system becomes infinity. Whereas if I put Z as infinity, 1 upon infinity is 0. So Z infinity value is not creating any problem here, but Z is equal to 0. If I take that particular value, it makes my Z transform infinite. So all the values of Z are accepted except the value of Z is equal to 0. And with this analysis, we write the ROC statement as ROC is the entire Z plane. Entire Z plane means all the values of Z except the value at 0, because we have just understood that when z is 0, the z transform becomes infinite. So we should avoid going for z is equal to 0. So we therefore write the ROC statement for the given sequence as ROC is entire z plane. All the values of z are accepted except at z is equal to 0. Moving ahead to the next problem. The second sequence is having 5 samples, but the modification done over here is that there is an arrow below a particular sequence, particular number. There's an arrow below a particular sample, let me say. Arrow below a certain sample. Now what this arrow signifies here, we know that an arrow in a discrete time domain signal indicates this position of the sample at 0th time instant, correct? So it means that this is a sample which is located at 0th time instant. So definitely all the samples on the right hand side are the samples which are located at the positive time instants, and all the samples on the left hand side of the arrow indicates the samples which are located at negative time instants. So we have total 5 samples, right? -1 is the sample which is located at 0, whereas sample 2 and 4 are located at the positive time instants, and samples 2 and 3 are located at negative time instants. So with this understanding of the given input signal, we can easily write the Z transform limits, because Xn, the range of Xn governs the limits of the Z transform. So this is the equation of Z transform. Analyzing Xn, we have understood that there are 2 samples on the left hand side and 2 samples on the right hand side about the origin. So therefore Xn is actually extending from -2 to +2. So changing the limits from -2 to +2 and expanding the summation for this particular limit is shown here. So you could see here the expansion starts from -2, x of -2, z raised to 2, the power becomes +2 because n has a value -2, so minus of -2 becomes +2. So x of -2, z raised to 2, x of -1, z raised to +1, and so on. So this is the expansion for the given limits. The next step is, now we need to appropriately substitute the magnitudes of these particular samples. So x of -2 is 3, x of -1 is 2, x of 0 is -1, x of 1 would be 2, and x of 2 would be 4. So accordingly, we have substituted the magnitudes of these samples, and the Z transform is as shown. Now is the time to find the ROC. This is the Z transform. We need to now mention the appropriate ROC for which the Z transform exists. So we observe here that the Z transform has both positive powers as well as negative powers. The Z transform here is comprising of the powers of Z which are both positive as well as negative powers. So looking at the powers of Z, we can easily understand for which values of Z the Z transform would become infinite. So if we put Z as 0, we get the negative powers of Z makes a Z transform infinite. And if we put Z as infinity, the positive powers of Z makes a Z transform infinite. So the ROC statement would therefore be defined as ROC is the entire Z plane except at Z is equal to 0 and Z is equal to infinity. Because Z is equal to 0 is making the Z transform infinite. Also Z is equal to infinity, that is positive powers of Z makes a Z transform infinite. So except these two values, all the Z values is accepted, and hence we write the ROC statement as ROC is entire Z plane except at Z is equal to 0 and Z is equal to infinity. Moving ahead with the next example, let us now find Z transform of a third sequence. Now what is the difference here? How is this particular sequence different from the earlier two? So again here we have an arrow
but the arrow is put on the extreme right sample. So it means that all the samples are lying on the negative time instance, and hence I can now say here that my given sequence xn is completely left-handed signal. It's a completely left-handed signal. All the samples are on the left-hand side of the arrow, so therefore the given sequence is entirely a left-handed signal. Now let us find the Z transform of this particular signal. Looking at the xn, right, we can define what would be the change in the limits. So as xn is entirely a left-handed signal, so this is a sample at 0, sample at -1, sample at -2, -3 and -4. It means that the limits or the xn actually is existing from -4 to 0 only for these time instants, and therefore the limits in the summation now modifies from -infinity to +infinity to -4 to 0. Why? Because my signal xn, my given signal xn is existing only for these time instants, and therefore the limits are modified from -4 to 0. The next step now is to simply expand the summation for various values of n. So let us now substitute n as -4, -3, -2, -1 and 0. For these particular values of n, we have expanded the summation as shown here. In the next step, we have appropriately substituted the sample magnitudes, and this is the equation of Z transform we have obtained for the given sequence. It's now the time to define the ROC where the Z transform actually exists. So we observe here that the Z transform has only positive powers of Z. There is no negative powers of Z, and therefore the value of Z which can make the Z transform infinite is infinity. If I put Z as infinity here, the whole Z transform becomes infinite, which should be avoided. And hence we write the ROC as ROC's entire Z plane except at Z is equal to infinity. We should not take this particular value of Z, because if we consider this particular value, the Z transform becomes infinite. Z transform, such a Z transform is not accepted, as Z transform becomes infinite at that particular value of Z, and hence it should be avoided. And therefore we write ROC is entire Z plane except at Z is equal to infinity. So let us once again, before we move ahead with a few more examples on Z transform, let us have a close analysis of these three particular problems of discrete time signal. Right, so in the first case we observed that the signal was entirely right-handed. Right, all the samples are on the right hand side. So when the samples are on the right hand side, we observe that the Z transform is having a sequence of all the Z values to be with negative power of Z. Right, so whenever a sequence in the Z transform has negative powers of Z, we can now easily correlate that the given sequence is completely right-handed. So right-handed sequence has negative powers of Z in its Z transform. Right? Observing the second, let us make certain conclusion. In the second example, we observed that the given sequence is a two-sided sequence. So it has samples on the right hand side, also on the left hand side. So it's a two-sided sequence. So if your sequence is a two-sided sequence, your Z transform comprises of the Z elements with both positive as well as negative powers of Z. Going in a reverse way, if you observe that your given Z transform is having both positive as well as negative powers of Z, how would you interpret that your given sequence must be a two-sided sequence? In the third case, we observe that the given sequence is entirely left-handed. All the samples are on the left-hand side. Such a sequence has a Z transform with all positive powers of Z. So all positive powers of z helps us to analyze that the given sequence, if I go back from z transform to my sequence, observing the z transform, if I observe that my z transform has only positive powers of z, then the sequence is entirely a left-handed sequence. So this way, friends, we can easily correlate the input with the z transform that we obtained. Or if I now know my z transform, I can make a complete clear prediction of how my input sequence would be. So if my sequence has only positive powers of z, I can understand. If my z transform has only positive powers of z, I can make a quick analysis that my input sequence is entirely a left-handed sequence. If my z transform has only negative powers of z, I can make a conclusion that the sequence is completely, input sequence is completely right-handed. And if the z transform comprises of both positive powers of z as well as negative powers of z, we can clearly make an analysis that the input sequence must be a two-sided sequence. Moving ahead with an example of z transform, xn is a raised to n un. Now we are coming to an example wherein we are solving applying z transform to infinite sequence. Now whatever three examples we just have discussed were applied to finite sequence. Now let us discuss an example of z transform where we are applying it for infinite sequence. So here an a raised to n un is an input sequence which is of infinite duration. Un is a standard signal, unit step signal, right? So indicating that it is extending from 0 to infinity, entirely right-handed sequence, infinite right-handed sequence. Okay, so let us try to find the z transform of such a sequence, infinite sequence. So starting with the z transform equation, this is the z transform equation. Let us now substitute our given xn. So xn is a raised to n un. Un here plays a crucial role in deciding the limits. So we know that un has magnitude 1, so it's not going to affect the magnitude of a raised to n, but un definitely plays an important role to decide the limits in the summation. So as un is entirely a right-handed sequence, it modifies the limits in the z transform, making it entirely right-handed, extending from 0 to infinity. So limits now extend, instead of minus infinity to plus infinity, the limits of the sequence extend from 0 to infinity. Un is 1. So what leaves in the summation is a raised to n, z raised to minus n. Let me collectively write both the terms as it has a common power. We will write it as a z raised to minus 1 raised to n. Now we need to simplify this summation. For this, we'll go for using the identity of summation. So identity of summation that can be applied to solve this z transform would be any summation n goes from 0 to infinity, a raised to n is 1 upon 1 minus a. So we'll use this summation identity, we'll apply this identity to solve this particular summation. So it's very similar to the identity a raised to n. Here my a raised to a term is a z raised to minus 1. So if I apply this identity here, right, if I apply this identity here, what do I get? I get 1 upon 1 minus a. So what is my a term here? A is this, a z raised to minus 1 is the term here. So what do I get? 1 upon 1 minus a z raised to minus 1. If I apply this identity here, right, it turns out to be 1 upon 1 minus a z raised to minus 1. My a term here is a z raised to minus 1. So this is my term here. Correct. So if I use this identity, this is what I get. Now before we discuss this further, it's time to identify the ROC. Now for finite sequences, we identified those values of z which made the z transform infinite. On the same lines here, how would we identify the z values? Here the simplest trick that would be that we could apply to find the ROC would be, right, to avoid those values of z which makes this particular z transform to reach a value of 1 by 0. So we know that the moment this particular z transform becomes 1 by 0, there is a chance of getting infinity. So we need to avoid that particular situation of arising 1 by 0. So when are we going to get 1 by 0? So the more, if z takes such a value, right, wherein it becomes it reduces to a value of 1. If this particular term reduces to a value of 1, so 1 minus 1 in the denominator would make it 1 by 0 reaching to infinity. So we need to avoid it. So the condition that should be applied so that we avoid infinity condition is that this particular term a z raised to minus 1 should be less than 1. If we apply a condition that this particular term a z raised to minus 1, if it is always less than 1, so there will never be a situation that we get 1 by 0 in the denominator. So we will set the condition for a proper ROC. To get a proper ROC is that this particular term a z raised to minus 1 should always be less than 1. So what do we get? Mod of z raised to if I solve this further, mod of z raised to minus 1 is 1 by a, and therefore I get in terms of z, if I try to evaluate this equation now in terms of z, I would get it as mod of z is greater than a. Right? So we have put a condition that this particular term never reaches a value of 1. And how did we do that? We did that by setting a condition on this that it should always be less than 1. Then simplifying it and getting a condition in terms of z, we have obtained the ROC that ROC should always be, right, that the z value should always be greater than a. So if we have this value of z always greater than a, then this is the region where z transform exists, right? This is the region where your z ROC, this ROC means this is the region where your z transform actually exists. If we do not satisfy this, then there is a probability that that z transform may reach to a value of infinity, which is not acceptable. So how would we plot this particular ROC? So we know the z-plane. Now let us come back to z-plane that we discussed at the start. So z-plane is comprising of real part of z and imaginary part of z. Let us take, this is, let me say this is my unit circle, right? And a is a value which is something less than a. Then I get one more circle whose radius is a. Now where is my ROC existing? ROC should exist outside a. Correct? So you could see here. ROCF, these lines, the lines in the red is a sketch where ROC exists. So this is the region where ROC exists, and this is the region that should be avoided, right, inside A. So ROC exists outside A, which is highlighted as shown here. So the sketch quickly helps us to identify the region where Z transform exists. So Z transform exists in the region outside A. Right, so collectively now writing the result. So we had obtained Z transform as 1 upon 1 minus a Z inverse, simplifying it in terms of Z. So the final Z transform is Z upon Z minus a, along with mentioning the ROC for the given problem, which is ROC is mod of Z greater than a. Right, so this is the ROC for the given sequence. There's one more important thing that should be noted here, and what is that? The given sequence is an infinite sequence. Also, the given sequence is entirely right-handed, right? The given problem statement was a raised to n un. Un is a right-handed sequence. How is the ROC that we obtain for an infinite sequence, which is right-handed? So when we plotted this ROC, we observed that ROC is outside the circle. So whenever it is a right-handed sequence, that is, the sequence is entirely placed on the positive timestamps, ROC always lies outside the circle. So these are small things that should be noted when we are analyzing the Z transforms.